Okay, welcome to Massive Open online course on fluid flow operations. In this lecture, we will discuss something about flow of viscous fluid as a part 1, and we have previously discussed about the basic principles of fluid flow operations and what are the governing basic equations by which we can represent the fluid motion by mass conservation, energy conservation and momentum conservation equations. And that the equations basically used for non-viscous fluid. Now, if there is a viscous fluid in case of real fluid, that how this fluid will be behaving and also what should be the governing equations, that we will discuss here. And in that case, one important equation, it is called the Navier-Stokes equation, and how this Navier-Stokes equation can be derived, and what will be the final form of the Navier-Stokes equation, and how this Navier-Stokes equation can be used to represent the application of different fluid flow in different processes. So, let us have the derivation of this fluid flow operations for this viscous fluid flow in this lecture. Before going to that, we have to know what is that viscous flow. Now, the ideal fluid is non-viscous, you know that we have already discussed in our previous lectures, and with the ideal fluid, that assumptions that we have made and discussed, that the basic equations of the flow of mass conservation by equation, even energy equation, that is mainly Bernoulli's equations, and how it is derived actually we have discussed. Also momentum equation, in the previous lectures we have derived the momentum equation as well as its application in different processes, like how jet pump is working on that momentum equations, and also how jet, even what is that other applications of this momentum whenever fluid is thrusting on a solid surface, how that momentum will be changing in its fluid directions, and also how this force will be balanced by that solid surface in opposite direction, that is that means opposite directions as per Newton's third law. Now, in that case, of course, those are you can say that ideal fluid, that is non-viscous, but in case of viscous fluid, that necessary in the practical, that no fluid will be that non-viscous. All the fluid in the real fluid, it will be viscous. So, there will be no fluid that will have zero viscosity. And also we can say that we can call this fluid which has that viscosity as a real fluids, and the flow of that real fluids is known as practical or viscous flow. And due to this viscosity of this real fluids, that will differ from the non-viscous ideal fluids, and this viscous fluid will offer some frictional or shearing resistance to the motion of the fluid. Even whenever it will be in motion, you will see there will be some angular deformations of the fluid element will occur. So, whenever we will go to derive this Navier-Stokes equation there, so we will consider that what will be the shear stress, angular deformation, elongation, contraction, and also mass conservation equation. They are also when different forces that acting on the fluid body, that will be discussed. And also, if we continuously supply energy which will be required to overcome this shearing resistance, whenever any viscous fluid will offer some resistance to flow. So, this is called viscous, which will be really totally different in case of real fluid compared to the ideal fluid. Now, we have discussed that what is that basic principles of that ideal fluid like continuity equation, energy equation and the momentum equation earlier. So, those basic equations of course, will be required here to discuss this viscous flow, and main viscous flow is called that is real fluid flow, and which will be representing by the Navier-Stokes equation. So, in that case you have to consider some fluid element in the fluid flow to represent its flow, even what should be the velocity, even how this velocity will be changing in the x, y and z direction, and also how this pressure will be changing, and how angular deformation will occur in this case. Now, if you look at this figure like this A, and this A figure will show you that some elementary rectangle of the fluid of side dx and dy, and dx dy, except this dx dy, you can have other directions in the z direction, whose length of course will be considered as dz, which is here perpendicular to this slide. So, if we consider that elementary rectangle of fluid of side dx, dy and dz, dz is as a thickness, we can apply the Newton's second law of motion here. So, in this case, if we consider that the velocity of the fluid element as u in the x direction, then within a strip of this element, that means of thick of side of length is dx, then from this side at a distance dx, what should be the velocity change? That will be u plus dou u dou x into dx. So, this is your change of velocity in the x direction. Similarly, in the y direction it will be changed if it is at this space the velocity is v, and at a distance of dy of this strip, then what should be the velocity? It will be v plus dou v dou y into dy. So, this will be your representation of the velocity, how it will be changing for a small strip of fluid element of side dx, dy and dz. And similarly, we can represent the pressure change in the x and y direction, like in the x direction, if we apply some pressure here as P, then in the other side of this stream, what should be the pressure will be acting? That will be increase of pressure or decrease of pressure based on that fluid element, the movement. So, it will be P plus dou P dou x into dx. So, in this x direction at a strip length of dx, the change of pressure will be P plus dou P dou x dx. Similarly, in the y direction, we can say that pressure will be changing from this P to P plus dou P dou y into dy. Dou P dou y is the pressure gradient in the y direction. Similarly, dou P dou x is the pressure gradient in the x direction. So, total here in this phase, what should be the pressure change? That will be equal to dou P dou x into dx. This will be your pressure change, that means how much pressure will be increasing or decreasing in this space. Again, if we represent the angular deformation, whenever fluid will be moving at a certain direction, you will see due to this viscous effect, you will see there will be a deformation of the fluid, that means surface, or you can say fluid layer over another one. So, in that case, if we suppose have this suppose due to this viscous effects and its flow, if there is an elongation like this in this direction, then you will see how this surface of this fluid element will be deforming from its original position. So, this is the angle at which this deformation of the fluid element will occurs at a certain velocity. So, it can be represented by this shear stress, even also you can say that that will be your shear strain also. So, shear stress will be changing in this direction, that will be represented by tau. So, tau in this x direction will be changing as tau plus dou tau dou x into dx, and here in this y direction tau will be acting as tau plus dou t dou y into dy. And the angular deformation, if we consider that angles that have made after this deformation, it will be as in this side it will be gamma 1 and in this side it will be gamma 2. then the rate of deformation of this angular angle, that will be called as angular deformation. This angular deformation will be represented by dou gamma dou t or d gamma dt. How much angle will be changed with respect to time whenever it will be flowing within a short period of time, that elementary element, and it will be changed because of this viscous effect. Now, if we see this diagram here, very interesting that there will be some elongation deformation in this x direction whenever you are stressing this fluid element in this x direction or y direction. You will see in the x direction, if you are stressing that, there will be a contraction in this y direction, whereas elongation will be in the x direction. Again, if you suppose stress this y direction, the contraction in the x direction and elongation will be in the y direction. Now, that elongation will be represented by this dou gamma dou t, and in this case the dotted line after elongation it will come. So, here if we represent this as unit of this length as 1 1. So, if it is elongated after elongation, if the position is like this, and before elongation if it is suppose like this, then what will happen? You will see there will be a formation of this elongation with this time t. So, this will be represented by dou gamma dou t. We will show later on that how related with this velocity with this elongation. Later on we will derive. Okay. First of all, we try to understand what is this actually. So, here see in this direction x direction there will be some force applying, and because of which there will be this, there will be a change of elongation, angular deformation, elongation, even something contraction also. Now, after this elongation or contraction, if we represent this by this dotted line, then how we can represent it here? Yeah, this to this length, okay, it will be your root over 2. Why this will be root over 2? Because this length and this length is considered as a 1 unit and 1 unit. So, this one will be your root over 2, that means root over 1 square plus 1 square, this will be root over 2. And of course, in this case due to this elongation velocity, the velocity gradient is dou u dou x. So, this one will be coming as again root over dou u dou x, because in this direction it will be, what is that, in the y direction there will be dou u dou x, and in this x direction it will be dou u dou y. So, similarly, you can calculate what will be the portion of this length, that will be root over 2 dou u dou x. Now, D represent here the relation between this tensile stress and the shearing stress. This sigma x is called tensile stress and tau is called shearing stress by this elongation transformation of in the x direction. Now, velocity of the angular deformation by the elongation is represented in figure E, and in this case if you are considering that contraction, that also you can have instead of elongation. So, in the same way, the same angle of deformation will happen whenever it will be contracting by stressing, and in the other way it will be elongated in the same angle. Now, due to this elongation, there will be a contraction or elongation at a certain length. So, that length will be changing with respect to time, that will be your dou u dou x. So, this will be your dou u dou x, here also negative of dou u dou x. Here also this contraction, if it happened, then here it will be your dou u dou v dou y, even this one also minus dou v dou y. So, if we represent this, suppose in the x direction there will be a contraction, that contraction will be represented by this here dou u dou x, and here in the y direction it will be dou v dou y. Since the contraction in the y direction is in the negative direction, so it will be actually represented by negative sign. So, it will be minus of dou v dou y. Now, the elongation and contraction both will be same. So, that is why dou u dou x into 1, that will be equal to minus dou v dou y into 1. So, this will be same there. So, contraction and elongation both will be in the same in scalar size. Next, of course, whenever fluid will be flowing, that fluid element will bear some force there. So, what are those forces that are acting on that element in x, y and z directions? So, those force will be represented by F. So, F in x direction, that will be F x, F in y direction, that will be F y, and F in z direction, it will be F z. And this the components of this force in x, y and z directions will be represented by this equation 1. Now, F x will be equal to, you know, that m into, that is mass into acceleration. So, mass is rho into dx dy dz. Rho is the density of the fluid, dx dy dz is the volume of the fluid. So, density into volume, it will be mass, and du by dt, it will be your acceleration. So, mass into acceleration, that will be your force. So, F x in the x direction, the force will be like this. Similarly, the F y, that means in the y direction, what should be the force, that will be represented by again this mass into acceleration in the y direction, that will be dv dt. Similarly, F z, the force acting in the z direction, that will be mass into acceleration in the z direction, that will be your rho dx dy dz into acceleration in the y direction. Here u, v and w are the velocities in x, y and z directions respectively. So, right hand side of equation 1, that will express the inertial force which is the product of the mass and the acceleration of the fluid element, and the change in the velocity of this element is brought about both by movement of position and by the progress of time. So, in this way we can represent the force. Now, if we consider this du by dt here, what should be that du by dt here? First of all, the velocity change at time dt can be expressed by this equation here. This du will be equal to the x, y and z direction component, then it will be dou u dou t into dt plus dou u dou x into dx plus dou u dou y into dy plus dou u dou z into dz. So, this is your velocity change at time dt. Now, if we divide both sides by dt, then we will get here du dt, that will be equal to dou u dou t plus dou u dou x into dx by dt, and dou u dou y into dy by dt here. So, it is here, and this one this, and this one here, and this one here, and this one you are getting like this. So, finally, you can represent it as what is that dou u dou t here, and in this case dx by dt will be represented by u, that means in the x direction what will be the velocity of this fluid. So, here u into dou u dou x, and this dou u dou x is the velocity gradient in the x direction there. Similarly, it will be v plus b into dou u dou y and w into dou u dou z. So, this is your, from this du expression you can express what will be the acceleration in the x direction. Similarly, in the y direction what should be the acceleration. So, it will be dv by dt. Similarly, you can have this dou v dou t plus u into dou v dou x plus v into dou v dou y plus w into dou v dou z. By substitution or by dividing this dv, if you are representing dv by dt from this equation. Similarly, in the z direction what will be the dw by dt, that means the acceleration in the y direction, that will be coming as dou w dou t plus dou w dou x into dx dt plus dou w dou y into dy dt plus dou w dou z into dz dt, that will be equal to dou w dou t plus u into dou w dou x plus v into dou w dou y plus w into dou w dou z. So, this 2, 3 equation number 2, 3 and 4 you can have the representation of acceleration in the x, y and z directions respectively. Now, after substitution of these acceleration terms du dt, dv dt and dw dt, we can have this force in the x direction as mass into acceleration. This acceleration terms we are substituting here, and then f y, that will be equal to mass into again that acceleration terms from equation number 1, Here Fz also, this is the equations for the force balance here Fz, and this is your equation number 1. If we represent this Fx, Fy and Fz by substituting this dy, dv, dt, this is acceleration terms, then we are getting this equation number 5 to express the force in x, y and z directions respectively. After that, now a question is that force is applying, what type of force actually applied in the acting on this fluid element. There are different types of forces that could be acting on the elements. That forces comprises of this body force, pressure force and viscous force. The body force will be represented by here F b, and this F b will have 3 components of this body force in the x, y and z directions, that will be represented by F into b x, that is as a function of, that is b x, b y, b z. That means in the x, y and z directions the body force will be b x, b y, b z. Similarly, pressure force in the x direction, y direction and z direction, it will be p x, p y and p z, and total force resultant pressure force will be F p there in the element. And the viscous force, this F s, it will be the viscous force, and again it will have 3 components in x, y and z directions. It will be S x, S y and S z. And in this case very interesting then that in the x direction, particularly in the x direction, what should be the total force acting on the fluid element. So, in the x direction, this F x will be equal to that summation of body force in the x direction, pressure force in the x direction and viscous force in the x direction. So, total in the x direction the force summation of this body force, pressure force and viscous force in this particular x direction. Similarly, in the y directions the summation of components in the body force, pressure force and viscous force in y direction to be considered here. Similarly, F z in the z direction, what should be the summation of components of these x, y and z directional components, out of which in the z directional components will be added for this body force, pressure force and the viscous force there. So, in this way by equation number 6 we can represent the total force in the x direction, y direction and the z directions there respectively. Now, what should be that body force, how this body force will be calculated. Now, this force actually act directly throughout the mass. So, such that the gravitational force it will be there, centrifugal force it will be there, or other different types of forces, electromagnetic force etc. Now, if we substitute this x, y, z as the these forces as the x, y, z axis components of such body forces. So, body forces will be represented as here x, y and z in the z direction, then the b x can be represented as what is that here x into rho dx dy and dz. So, this will be your body force in the x direction. What is this here force into what is that this here rho into dx dy, that means here mass into acceleration, that will be your x. Similarly, here by it will be y into rho dx dy dz. Similarly, bz will be equal to z rho dx dy dz. So, in this way if we put this x, y, z as a acceleration of components in the x, y, z directions, and then body force will be calculated by this equation number 7 in this way. The pressure force again will have 3 components like P x, P y, P z. So, P x will be calculated if you look at this picture here, that if pressure force is acting on the surface of this fluid element in the x direction, then here in the x direction what will be the force acting here, what is the cross sectional area, that will be dy dz, then what will be the pressure, then what will be that total force in this acting in this space, then it will be P into dy dz. Similarly, the opposite side the pressure will be acting in the opposite direction, it will be P plus dou P dou x dx into dy dz. So, this is your in the opposite. Similarly, in y direction in this you will get, and here in this direction you will get this pressure differences there. So, if we have this pressure, that means here effective pressure in this x direction, it will be P into dy dz minus of this, that means here P plus dou P dou x into dx into dy dz. So, it will be here, and after subtracting these components, finally, it will be coming as minus of dou P dou x into dx dy dz. Similarly, in the y direction, if we have this balance of these pressure forces, it will be P y, it will be equal to P into dz dx here, dz dx y, because this one is your dz and this is your x. So, this will be your dz dx. So, here pressure force will be in this direction, it will be what, that P into dz dx. Similarly, from the other side of this y direction, it will be P plus dou P dou y into dy, then it will be into dz dx. So, finally, after subtracting, you can get this minus of dou P dou y into dx dy dz. So, similarly, if you calculate the pressure force in the y direction, then you can have this P z will be equal to what, minus dou P dou z into dx dy dz. So, in this way we can easily calculate what should be the pressure force, and in the x, y, z direction what will be their components. Now, considering that viscous force, this viscous force is little bit complicated, because whenever the fluid will be flowing, there will be a frictional force, and because of which viscous effect, you will see there will be angular deformation, and this deformation will be sometimes, you know that two types of here. What is that? We have discussed earlier that there are two components of this force. One is called here, that is I think you told that one is tensile stress and another is shearing stress. So, we have discussed in this figure what is the tensile stress and shearing stress. Now, if we first consider these forces are there because of this angular deformation of this fluid flow in the x direction, what should be the force? Now, putting the strain of the small element of fluid gamma, then here the corresponding stress will be expressed as by this. So, here it will be tau will be equal to tau x y plus tau x z. So, in this case this is in the x direction. So, it will be mu into what will be that rate of deformation here, viscosity into here, this is the coefficient of viscosity, and d dou gamma dot is the angular deformation here. So, finally, you will get this how to calculate this dou gamma dou t here. Dou gamma dou t, it is actually by mu into dou u dou y plus dou v dou x, and plus dou u dou z plus dou omega or dw dx. So, similarly, here S x 1, that means here what will be the angular deformation, that will be equal to dou tau x y dou y plus dou tau x z dou z into dx dy dz. And finally, if you substitute this tau x y tau x z there, then you can have this. Now, at steady state condition or in the only two dimensional case, you will see that in the z directions there will be no stresses or angular deformation. So, in that case this part will be equals to 0, and then finally, you are getting this mu into dou u dou y square minus dou u square u by dou x square plus dou 2 u by dou z square into dx dy dz. So, this is your S x 1, that means called the force in the x direction, that will be due to the angular deformation. And what should be the force in the x direction due to the elongation transformation there, due to the stress, that means here elongation or contraction. Consider the rhombus here of EFGH that inscribed in a cubic fluid element of ABCD in this figure of unit thickness, if you are considering as shown in this figure, and which will show you an elongated flow to the x direction, and also parallelly a contraction flow in the y direction. So, this deformation in this x and y directions that will produces a simple angular deformation that is seen in the rotation of the faces of this rhombus here. So, whenever it will be rotating, then of course, you will get this deformation because of this elongation and contraction. So, you have to consider what should be that elongation and how this elongation or contraction rate or angular deformation rate will be changing in the x and y directional components of the fluid velocity. Now, in this case calculating this deformation per unit time, the velocity of angular deformation that means d gamma by dt, that will become here this root over 2 dou u dou x divided by root over 2. Since here in this case finally you can get dou u dou x. So, this is your what is that here in this direction what will be the value for this, here it is given this direction, here it is given what should be that root over 2 into dou u dou x, and here this is your root 2. So, this here this is your before elongation or after elongation, what is that how from this what will be the angular deformation, from this how it will be coming from. So, after if it is suppose in this direction there will be an elongation. Now, after elongation this will be changing at root over 2 dou u dou x, and this was your by initial length. So, final divided by initial, that is increment, and this will, so it will get the elongation angular deformation. So, it will be dou u dou x. Therefore, a shearing stress that acts on the 4 faces of the rhombus EFGH here. So, in that case tau should be represented as mu into dou gamma dou t. So, that will be equals to mu into dou u dou x, that will be based on this angular deformation. So, by equation 12 you can represent this shear stress. Similarly, for equilibrium of the face, that force acting on these faces to equilibrium condition, that means for equilibrium of the force on the faces, that E z due to the tensile stress sigma here as per this diagram shown. Then the shear force tau on this E h, and here see E h in this figure, E h then this how that is shear forces tau on the E h and H g, how it will be there, what will be the value in that case. Sigma x will be the representation of this equilibrium tensile stress. So, this tensile stress in this x direction, it will be equal to 2 into root over 2 tau cos 45 degree as per geometry. Here it will be coming as 2 tau. So, sigma x will be equal to what? 2 mu into dou u dou x here. So, this is your tensile stress. So, we got this shear stress here as mu into dou u dou x, whereas this tensile stress is 2 into mu into dou u dou x, that will be 2 times of this shear stress here. And if we consider the fluid element that having sides dx dy and thickness dz, and the tensile stress in the x direction on the face at distance dx, that will become what is that sigma x plus dx, that will be equal to sigma x plus dou sigma x dou x into dx. This will be your incremental tensile stress. So, at this x plus dx what will be the tensile stress, you can obtain from this equation number 15. Now, after getting this equation number that is equation for what is the tensile stress and shear stress, then the tensile stress in the x direction acts on the face of area, that dz dy. So, finally, we can calculate the force S x 2, that is called tensile stress in the x direction. So, that will be equal to minus sigma x x into dz dy plus sigma x x plus dx dz dy. Then what will be the, after subtracting, it will coming as dou sigma x dou x into dx dy dz. So, it will be equal to 2 into mu into dou u dou 2 u dou x square into dx dy dz. So, this is your final S x 2. S x 2 is what? S x 2, what we have represented this S x 2? We called it that force in the x direction due to the elongation transformation. So, this elongation transformation you can have from this equation number 16 in the x directions. So, we can summarize it in the x direction, it will be what is that S x 1 and S x 2. What is S x 2? This is S x 1 is the elongation transformation and S x 2 is the what is that angular transformation or angular deformation, elongation transformation, and other S x 1 is the what is that angular deformation. So, S x 1 is the angular deformation that is force acting in the x direction, and this is your elongation transformation as x x 2. So, here S x 1 and S x 2 angular and elongation, these two transformation to be added in the x direction to get this tensile stress here. So, in this tensile stress or in the x direction we are getting this equation here, similarly this here, and for z direction this will be your equation. So, equation 17 will give you that S x, that will be equal to S x plus S x, S x 1 plus S x 2. So, finally, you are getting these things. Now, after substitution of this body force, even pressure force and tensile what is that force due to this angular deformation, if we substitute all those components in equation number 1, then we can get what is that, we can finally represent it by this equation here, rho into dou u dou t plus u dou u dou x plus v dou u dou y plus w dou u dou z is equal to rho x minus dou p dou x plus mu into dou 2 u dou x square plus dou 2 u dou y square plus dou 2 u by dou z square. So, this is your equation based on this substitution of S x 1 and S x 2 and also this pressure forces and then body forces and these body forces, then after substitution all these equations here in equation number 5, then we can have this final form of equation here like this this one. So, this whole equations will be called as what is that Navier-Stokes equation. These equations is being used for actually assessing different fluid motion in viscous flow. And these equations have I think 4 components here. This part is called inertia terms, here this part is called inertia, and this part it is called that body force term, and this terms is called pressure term, and these are called as what is that viscous term. So, this Navier-Stokes equation will have total 4 terms, that is one is inertia, another is body force, pressure force and the viscous forces. So, all those things will be considered whenever you are representing any fluid motion in a general way, that you have to calculate based on the assumptions whether these components will be there or not. Based on these equations, you can finally get some equation to represent the fluid motion. And this Navier-Stokes equation can also be represented by other system like cylindrical coordinating system. So, in that case it will be represented by this equation, and in that case sigma r r in the direction, that is cylindrical coordinates, and this one sigma theta theta, sigma z z, and tau r theta, tau theta tau, and what is that tau j tau. So, these are the final equations for the Navier-Stokes equation in the cylindrical coordinate system, and you can apply also these cylindrical systems for the particular operations either by Cartesian coordinates and even by cylindrical coordinates. And other components of this here cylindrical coordinates for this Navier-Stokes equation is r component, theta component, and the z components will be represented by these equations. And like one examples, let us have an example like if any liquid flow downward through an inclined plane of surface in a steady fully developed laminar film of thickness h as shown in figure here in this. And in this case can you write the continuity and Navier-Stokes equations simplified to model this flow field as per assumptions here. What is that assumptions here? It is a steady state flow, and incompressible flow, in that case of course density will be constant, and here no flow or variation of properties in the z direction. So, W is equal to 0, and fully developed flow. So, no properties vary in the x directions there. So, if we apply this Navier-Stokes equation based on these assumptions, we can have this in dou u dou x will be equals to 0 and dou u dou z will be equals to 0. So, only these terms will be remain there in the continuity equation. So, it will be coming dou u dou y will be equals to 0. Other terms in this case, here you will see this terms will be 0, this terms will be 0, this terms will be 0, this terms will be 0 as per assumptions. So, here only thing is that rho z x in the x direction, what will be the gravitational force components, and here dou p dou x will be equals to 0 because there will be no change of pressure in the x direction, and there will be no what is that here viscous force in this x direction, but there will be viscous force acting over this y direction. That means, here there will be velocity gradient in the y direction due to this viscosity, and that is why these components will be remain same in the x direction. And other in the y and z directions, here all other terms are here like this one will be cancelled, this one will be cancelled, this one will be cancelled, and in the y direction of course there will be a gravitational force. So, you have to consider this, and also in the y direction in this case there will be a in the y direction there will be a pressure gradient. So, that you have to consider, other terms will be neglected, and here in the z direction no other things will be considering here, but in the z direction dou p dou z will be considered here in the z directions. Here also you can say in the z direction there will be a certain change of pressure. So, this one will be cancelled out. If you are not having any pressure gradient in the z direction, then you can also neglect this dou p dou z here. So, finally, continuity equation we are getting this one dou u dou y will be equals to 0, and as per Navier-Stokes equation, after simplification we are getting here rho z x plus mu into dou u dou y, that will be equals to 0. Similarly, here 0 will be equal to rho z y minus dou p dou y, this one. So, these two equations based on the Navier-Stokes equation, and finally, from this equation you can have this dou d 2 y by dy square, that will be minus rho g x mu. Now, this g x in the x direction, as per diagram here, the x direction what is the, here we are considering this x direction in this here the that is parallel to the flow and perpendicular to the flow, that is y direction. So, based on this, what should be the components in the y direction, what will be the velocity components or pressure components or gravitational force components there, that you have to calculate. If I consider this what is that g x here in this x direction, what will be the g x, that will be g into sin theta there. So, ultimately we are getting rho into g into sin theta by mu, that will be your Navier-Stokes equation based on this x directional flow. So, this will be your change. So, from this equation further you can calculate to have the velocity distribution, and from this you can have the pressure also by this equation. Another examples, if it is suppose cylindrical coordinates, how it will be there. If suppose any laminar viscometric flow of liquid in annular gap between vertical concentric cylinders as shown in figure there, the inner cylinder is to be considered as stationary, and the outer cylinder rotates at a constant speed there in this case. While this flow of this outer cylinder, there will be some viscosity acting over the surface of this inner cylinder. So, in this condition you have to actually simplify the continuity and Navier-Stokes equation based on these assumptions given below here. It will be considered as a steady flow, and angular speed of the outer cylinder is constant there, and the flow is what is that incompressible, that means rho is constant, and also there will be no flow or variation of the properties in the z direction. So, V z and dou z will be equals to 0. Similarly, circumferentially if you are considering that symmetric flow, then there will be no change of properties that will vary with the theta direction, and so dou theta will be equals to 0. So, under these assumptions we can have this based on the cylindrical coordinates of this continuity and Navier-Stokes equation. This will be continuity equation, and this Navier-Stokes equation with r component and this theta component and z. This marks is actually considering that here this marks this is 0 based on these assumptions. So, please go through this again and see, you will see how this dou V r dou t will equals to 0 this based on these assumptions. But here the theta direction there will be a velocity change with respect to r. So, you have to consider that things, and other parts here with respect to r, that the pressure also will be changing. So, that part also you have to consider here, and other things here in this components in the y theta components here. So, this viscous terms will be considered here, and in the z directions only this gravitational force and this what is that pressure force in the z directions will be considered, and the shear stress in r and theta directions, then there will be shear stress here. So, based on which you can calculate further what will be the velocity distribution. Those problems, this velocity distribution, pressure change, all these things will be actually represented in the next class with an example also. So, here finally, you can get the continuity equation that will be reducing after simplification this equation, and this here this is the pressure, and this will be your viscosity based on viscosity V theta component. And here based on this we can then further calculate the what is that to obtain the governing equation for this what is that final form of equation for pressure and the components of the velocity in the r and theta direction. So, I will suggest to practice this lecture again and again to understand the governing equations, how it has come, and also try to just imagine how you can actually write this Navier-Stokes equation here without just seeing all this here. Just try to practice here, try to write yourself whether you can write the Navier-Stokes equation yourself or not. And then for a particular problem in the horizontal direction, if there is a flow, then how this Navier-Stokes equation can be applied, what will be the components, whether you can write or not, that you have to apply, and just based on your own understanding, okay, just you can write. You try to cancel that what is that part of velocity components or pressure components x, y and z directions, then you will get the simplified equation. After that you can go further for calculation, but based on this Navier-Stokes equation, you can, I think, have this governing equation for any flow there that will be flowing through the pipeline, channel or any other things. Okay. So, this is basically the lecture is basically the Navier-Stokes, how it is derived, and what will be the form of this Navier-Stokes equation, that will be here to be learned. So, I think you can read further for more understanding of this Navier-Stokes equation from these textbooks also, okay, and also practice it. Okay. So, that is for all today's lecture. Thank you.